In this lecture, we'll be discussing another solved problem on priority scheduling. So let us see what is this problem and how we can solve it. So here is a problem. Consider the set of processes with arrival times given in milliseconds, CPU burst time given in milliseconds, and priority as shown below. And here higher numbers represent higher priority. If the CPU scheduling policy is priority non-preemptive, calculate the average waiting time and average turnaround time. So in the previous lecture that we have discussed, we solved a problem that was based on preemptive priority scheduling. But this question is based on non-preemptive priority scheduling. And here we have to calculate the average waiting time and the average turnaround time for this set of processes with process IDs P1 to P5, where their arrival times given here in milliseconds, burst times given in milliseconds, and priorities given here. And also note that in this problem, higher number represents higher priority. So in the previous problem that we solved, the lower the value, the higher was the priority. But in this case, the higher the value, the higher will be the priority. So if you look at this priority list, 5 is the highest priority and 2 is the lowest priority. So I'm taking this example because you should be familiar with the different kind of problems that can be there. So in some cases, the lower number may represent higher priority, and in some cases, the higher number may represent the higher priority. So pay close attention to what the question asks, otherwise you may make a mistake. So given this information, our task is to calculate the average waiting time and the average turnaround time. So let's see how we can do that. So in order to solve the problem, I have copied down the same table here again. And the first step, as we have already discussed many times, is to form the Gantt chart for this set of processes. Now remember that in the question it was said that this is a non-preemptive priority scheduling. So when we say non-preemptive, what it means is when one process gets the CPU for its execution, then until and unless it completes its execution, no other process will take the CPU away from it. That means it will never be preempted. So keep this in mind when we are forming the Gantt chart. Alright, so let's see how the Gantt chart for this can be formed. So here is a Gantt chart for this set of processes P1 to P5. So let's see what happens. Let's see which is the first process that arrives. If you look at the table, we see that P1 arrives at time 0. So P1 is the first process to arrive. Since there were no processes at that time, and since P1 was the first one, it gets the CPU and it begins its execution. And how long will P1 execute? It will execute for 4 milliseconds because that is the burst time of P1. And then no processes will disturb P1 until and unless it completes its execution, because this is a non-preemptive priority scheduling. And also the priority of P1 is 2. So since there were no other processes at that time, we don't have to worry about the priority for this case. Now let's see. P1 is continuing its execution, and then at 1 millisecond, P2 arrives. And let's see what is the condition in our Gantt chart at that time. So at 1 millisecond, P1 is already executing. Now, if you see here, and if you check the priority, you see that it's having a priority of 3. Now, if you compare the priority of P1 and P2, we see that P2 has a higher priority. So keep in mind that in this case, the higher the numbers, the higher is the priority. So P2 has a priority of 3, which is higher than that of P1. But will it be preempted? It will not be preempted because this is a non-preemptive scheduling. So even though the priority of P2 is greater than that of P1, P1 will still not be disturbed. It will be allowed to continue its execution. So till the 4th millisecond, P1 continues its execution. So if you look at this table, we see that at 2 milliseconds, P3 also arrived, and at the 3rd millisecond, P4 also arrives, and at 4 milliseconds, P5 also arrives. So when P1 was continuing its execution from 0 to 4 milliseconds, at this portion of time, all the other processes have also arrived. And if you check the priorities, we see that P2 has priority of 3, P3 has a priority of 4, and P4 and P5 both has priorities of 5. And we see that all these priorities are greater than that of P1, which is 2. But even then, P1 will not be disturbed because this is a non-preemptive priority scheduling. So now we see that when P1 was executing from 0 to 4, all these other processes have already arrived and are now waiting at the ready queue. Alright, now at the 4th millisecond, P1 completes its execution. So P1 finishes his execution and the remaining processes are P2, P3, P4 and P5. Now they have all arrived and they are all waiting at the ready queue. So we don't have to worry about these arrival times anymore. So what we have to see is which among this set of 4 processes has the highest priority. So if we check here, we have 3, 4, 5, 5. So we see that P4 and P5, they are having the highest priority. So either P4 or P5 should be getting the CPU. Now if you look, we see that P4 and P5 has the same priority. So who should get the CPU? There is a tie over here. Now if we have this kind of a tie, in order to break the tie, we will be using the FCFS scheduling. That means the first come first serve scheduling. So if 2 processes are having the same priorities, then the process that arrived first among them will be the first to get the CPU. So if you see here, P4 arrived at 3 milliseconds and P5 arrived at 4 milliseconds. So P4 was the first one to arrive. So we will be giving the CPU to P4. So P4 gets the CPU and it will continue its execution for how many milliseconds? 5 milliseconds, because that is the burst time of P4. So from 4 to 9 milliseconds, 4 plus 5 is 9. So up to the 9th millisecond, P4 will continue its execution. So after P4 releases the CPU, who will get the CPU? It's obvious, it is P5, because P5 also had the same priority, but since P4 arrived earlier, the CPU was given to P4. So next, the CPU will be given to P5. And how long will P5 execute? It will execute for 2 milliseconds. So from 9 to 11, 9 plus 2, 11. Up to the 11th millisecond, P5 uses the CPU for its execution. Alright, so now we see that P1 completed, P4 completed, P5 also completed. So the remaining processes are P2 and P3. Now among P2 and P3, who has the highest priority? We see that P3 has a priority of 4, which is higher than that of the priority of P2, which is 3. So P3 will be the next one to get the CPU when P5 releases it. So P3 gets the CPU when P5 releases it. And how long will it execute? It will execute just for 1 millisecond, which is the burst time of P3. So from 11 to 12 milliseconds, P3 executes. And then the final process that we have is P2. So P2 will now get the CPU after P3 releases it at 12 milliseconds. And P2 will execute for 3 milliseconds, which is the burst time of P2. So 12 plus 3 is 15. So up to the 15th millisecond, P2 uses the CPU, and at this point all the processes have completed their execution. So this is how we form the Gantt chart for a set of processes when they follow a non-preemptive priority scheduling. So here, since it is non-preemptive, it is a bit easier to form the Gantt chart because you are not going to preempt any processes, but keep in mind the arrival times. See the arrival times and see the priorities. So in this case, when P1 was executing from 0 to 4 milliseconds, all the other processes already arrived and were waiting in the ready queue. So we just had to see the priorities of those processes and assign the CPU to them one by one based on the highest priority. So now we have the Gantt chart. Now what we have to do is we have to calculate the average turnaround time and the average waiting times. So in order to calculate that, first we have to calculate the turnaround times and the waiting times for these set of processes one by one. So let's see if we can recall the formula for that. So here is a formula. So these formulas are same as the ones that we use for some of the other scheduling algorithms when they follow the non-preemptive form of scheduling. So the turnaround time is the completion time minus the arrival time. So we need to see when a process completed its execution, and from that if we subtract the arrival time, then we get the turnaround time. And the waiting time is the turnaround time that we calculated here minus the burst time. That will give us the waiting time. So let us calculate the turnaround time and waiting time for all these processes one by one. Alright, so here we have a table in which we will be calculating the turnaround times and the waiting times. So first of all, we need to find out the completion times because that is required for calculating the turnaround time. So we have process with process IDs P1 to P5, the same thing. And let us see the completion times for this set of processes. So for P1, what is the completion time? So for getting the completion time, just look at the Gantt chart and see when the process released the CPU or completed its execution. So if you see P1, it completed its execution at 4 milliseconds. So that is the completion time of process P1. And for P2, what is the completion time? It is 15 milliseconds. And for P3, it is 12 milliseconds. For P4 it is 9 milliseconds, and for P5 it is 11 milliseconds. So this is very easy. Just look at the Gantt chart and fill this up. Alright, so let's calculate the turnaround time. So for process P1, what is the turnaround time? It is the completion time minus the arrival time. So what is the completion time of process P1? It is 4 milliseconds. What is the arrival time? It is 0 milliseconds. So what will be the turnaround time? It is 4 minus 0, which is 4 milliseconds. So similarly for P2, what is the completion time? It is 15. And what is the arrival time? It is 1 milliseconds. So what will be the turnaround time? It is 15 minus 1, which is 14 milliseconds. And for P3, what is the completion time? It is 12 milliseconds. And what is the arrival time? The arrival time of P3 is 2 milliseconds. So what will be the turnaround time? The turnaround time is 12 minus 2, which is 10 milliseconds. And similarly for P4, the completion time is 9. And then the arrival time is 3. So the turnaround time will be 9 minus 3, which is 6 milliseconds. And similarly for P5, the completion time is 11 milliseconds. And the arrival time of P5 is 4 milliseconds. So that gives us a turnaround time of 11 minus 4, which is 7 milliseconds. So hence we have found the turnaround times for the set of processes P1 to P5. Now we can calculate the waiting times. So the waiting times can be calculated by turnaround time minus the burst time. So we have already calculated the turnaround times. So from that we have to subtract the burst times from this table. So that will give us a waiting time. So let's see, for process P1, the turnaround time is 4 milliseconds. And what is the burst time of P1? It is 4 milliseconds. So what is the waiting time of P1? It is 4 minus 4, which is 0 milliseconds. So we see that P1 was the first process to arrive, and even though it had a priority of 2, since it was the first process to arrive and since there were no processes at that time, P1 was given the CPU and it did not have to wait at all. And since this was a non-preemptive priority scheduling, P1 was not disturbed until its execution was complete. So P1 did not have to wait at all. So that is why the waiting time of P1 is 0 milliseconds. So similarly for P2, what will be the waiting time? It is the turnaround time 14 minus the burst time of P2, which is 3 milliseconds. So that gives us 14 minus 3, 11 milliseconds. And for P3, it will be turnaround time 10 minus the burst time, which is 1. That gives us 10 minus 1, that is 9 milliseconds. And for P4, the turnaround time is 6, and then the burst time of P4 is 5. So that will give us a waiting time of 6 minus 5, that is 1 millisecond. And finally for P5, the turnaround time is 7 and the burst time is 2. So we have a waiting time 7 minus 2, that is 5 milliseconds. So we have also calculated the waiting time for this set of processes P1 to P5. So now calculation of the average turnaround time and average waiting times are very easy. So how do we do it? The average turnaround time is 4 plus 14 plus 10 plus 6 plus 7 divided by the number of processes, which is 5, which gives us 41 divided by 5, which is 8.2 milliseconds. And similarly, the average waiting time is 0 plus 11 plus 9 plus 1 plus 5 divided by the number of processes, which is 5. That gives us 26 divided by 5, which is 5.2 milliseconds. So our question was to calculate the average turnaround time and the average waiting times for this set of processes when they follow a non-preemptive priority scheduling, and we have done that. So even here we see that the most important thing is to form the Gantt chart, and after you form the Gantt chart, if you remember these formulas, we can easily calculate the turnaround times and waiting times and calculate the final answer. And even this formula, you don't have to memorize it. I've already explained how we come to this formula in the previous lectures. So using that, remember how we arrive at this formula and keep it in mind, and it will be very easy to proceed with this kind of calculations. So I hope the way we solved this problem was clear to you. Thank you for watching and see you in the next one.